Hi everyone, here we are going to discuss the design and detailing of RC shear walls. Proposed design provisions for shear walls. A requirement of this section apply to shear walls which are part of the lateral force resisting system of the structure. General requirements. First one, the thickness of any part of the shall not be less than 100 mm. And the second one, the effective flange width to be used in the design of flange wall sections shall be assumed to extend beyond the face of the web for a distance which shall be smaller of half the distance to an adjacent shear wall web and 1/10 of the total wall height. Shear walls shall be provided with reinforcement in the longitudinal and transverse directions in the plane of the wall. The minimum reinforcement ratio shall be 0.0025 of the gross area in each direction. This reinforcement shall be distributed uniformly across the cross section of the wall. Fourth one, if the factored shear stress in the wall exceeds 0.25 root FCK or if the wall thickness exceeds 200 mm, reinforcement shall be provided in two curtains, each having bars running in the longitudinal and transverse direction in the plane of the wall. Fifth one, the diameter of the bars to be used in any part of the wall shall not exceed 1/10 of the thickness of that part. And sixth one, the maximum spacing of reinforcement in either direction shall not exceed the smaller of LW by 5 or 3 TW and 450 mm, where LW is the horizontal length of the wall and TW is the thickness of the wall web. Next, we are going to discuss the shear strength requirements. The nominal shear stress Tv shall be calculated as Tv equals Vu divided by Tw dW, where Vu is the factored shear force, Tw is the thickness of the web, dW is the effective depth of wall section. This may be taken as 0.8 Lw for rectangular sections. And the design shear strength of concrete TC and TOC shall be calculated as per table 13 of IS 456. And the nominal shear stress in the wall tau v shall not exceed tau c max as per table 14 of IS 456, similar to other RC structures. When tau v is less than tau c, shear reinforcement shall be provided in accordance with 1.1.3, 1.1.4 and 1.1.6 clauses of this code. When tau v is greater than tau c, the area of horizontal shear reinforcement AH to be provided within a vertical spacing SV is given by VUS equals 0.87 FY AH DW divided by SV, where VUS equals VU minus tau C TW DW is the shear force to be resisted by the horizontal reinforcement. However, the amount of horizontal reinforcement provided shall not be less than the minimum as per 1.1.3. The vertical reinforcement that is uniformly distributed in the wall shall not be less than the horizontal reinforcement calculated as per 1.2.5. And that's all about the shear strength requirements. And next one, flexural strength. The moment of resistance MUV of the wall section shall be calculated as for columns subjected to combined axial load and uniaxial bending as per IS 456. The moment of resistance that is provided by uniformly distributed vertical reinforcement in a cylinder rectangular wall section may be calculated as follows. For XU by LW less than or equal to XU naught by LW, MUV divided by FCK TW LW square equals 5 into 1 plus lambda by 5 times half minus 0.416 XU by LW minus XU by LW square times 0.168 plus beta square by 3, where XU by LW equals 5 plus lambda divided by 25 plus 0.36 and XU naught by LW equals 0.0035 divided by 0.0035 plus 0.87 FI by ES. and phi equals 0.87 Fy rho divided by Fck, and lambda equals Pu by Fck Tw Lw, where rho is the vertical reinforcement ratio, which equals Ast by Tw Lw. And Ast is the area of uniformly distributed vertical reinforcement, and beta equals 0.87 Fy by 0.0035 Es, where Es is the elastic modulus of steel and Pu is the axial compression on wall. And the second case, for xu0 by Lw less than xu by Lw less than 1.0, muv by Fck Tw Lw square equals alpha 1 xu by Lw minus alpha 2 xu by Lw square minus alpha 3 minus lambda by 2, where alpha 1 equals 0.36 plus 5 times 1 minus beta by 2 minus 1 minus 2 beta, and alpha 2 equals 0.15 plus 5 by 2 times 1 minus beta square by 2 minus 1 by 3 beta, and alpha 3 equals 5 by 6 beta times 1 by xu by Lw minus 3. The value of xu by Lw to be used in this equation should be calculated from the quadratic equation alpha 1 times xu by Lw square plus alpha 4 times xu by Lw minus alpha 5 equals 0, where alpha 4 equals 5 by beta minus lambda, and alpha 5 equals 5 by 2 beta. The cracked flexure strength of the wall should be greater than its uncracked flexure strength, and in walls that do not have boundary elements, vertical reinforcement consisting of at least 4 bars of minimum 12 mm diameter arranged in 2 layers shall be provided along the edge of the wall. And the next section, boundary elements. Boundary elements are portions along the wall edges that are strengthened by longitudinal and transverse reinforcement. Though they may have the same thickness as that of the wall web, it is advantageous to provide them with greater thickness. Where the extreme fiber compressive stress in the wall due to factored gravity loads plus factored earthquake force exceeds 0.2 Fck, boundary elements shall be provided along the vertical boundaries of walls. The boundary elements may be discontinued where the calculated compressive stress becomes less than 0.15 Fck. The compressive stress shall be calculated using a linearly elastic model and cross-section properties. A boundary element shall have adequate axial load carrying capacity, assuming short column action, so as to enable it to carry an axial compression equal to the sum of factored gravity load on it and the additional compressive load induced by the seismic force. The latter may be calculated as mu minus muv divided by Cw, where mu is the factored design moment of the entire wall section, and muv is the moment of resistance provided by distributed vertical reinforcement across the wall section, and Cw is the center to center distance between the boundary elements along the two vertical edges of the wall. If the gravity load adds to the strength of the wall, its load factor shall be taken as 0.8. And the percentage of vertical reinforcement in the boundary elements shall not be less than 0.8% nor greater than 6%. In order to avoid congestion, the practical upper limit would be 4%. Boundary elements where required as per 1.4.1 shall be provided with special confining reinforcement as is required for columns in IS 4326. Boundary elements need not be provided if the entire wall section is provided with a special confining reinforcement as is required for columns in IS 4326. And that's all about boundary elements. And the next section is coupled shear walls. Coupled shear walls shall be connected by ductile coupling beams. If the earthquake-induced shear stress in the coupling beam exceeds zero point 0.1 ls root FCK divided by d, where ls is the clear span of the coupling beam and d is its overall depth, the entire earthquake-induced shear wall and flexure shall be preferably be resisted by diagonal reinforcement. The area of reinforcement to be provided along each diagonal in a diagonally reinforced coupling beam shall be ASD equals Vu divided by 1.76 Fy sin alpha, where Vu is the factor shear force and alpha is the angle made by the diagonal reinforcement with the horizontal. At least 4 bars of 8 mm diameter shall be provided along each diagonal. The reinforcement along each diagonal shall be enclosed by special confining reinforcement as is required for columns in IS 4326. And the pitch of spiral or spacing of ties shall not exceed 100 mm. The diagonal or horizontal bars of a coupling beam shall be anchored in the adjacent walls with an anchorage length of 1.5 times the development length in tension. That's all about coupled shear walls. The next section is openings in walls. The shear strength of a wall containing openings should be checked along critical planes that pass through openings. The reinforcement shall be provided along the edges of openings in walls. The area of vertical and horizontal bars should be such as to equal that of the respective interrupted bars. The vertical bars should extend for the full story height. The horizontal bars should be provided with development length and tension beyond the sides of the opening. And the next section, discontinuous walls. Columns supporting discontinuous walls shall be provided with special confining reinforcement as per IS 4326 over their full height. The column reinforcement shall be extended into the wall for a distance equal to the development length of the largest longitudinal bar in the column. The next section is construction joints. The vertical reinforcement ratio across a horizontal construction joint shall not be less than 0.92 divided by Fy times tau v minus Pu divided by Ag, where tau v is the factored shear stress at the point, Pu is the factored axial force positive for compression, and Ag is the gross cross-sectional area of the joint. The design shear force at the joint must be less than the shear force that can be safely transferred across the joint, Vj. This is calculated by the shear friction concept and is given by Vj equals mu times 0.8 Pu plus 0.87 Fy Av, where mu is the coefficient of friction at the joint, mu equal to 1.0, and Av is the area of vertical reinforcement available. To account for the possible effects of vertical acceleration, the axial load is taken as 0.8 Pu instead of Pu itself. The next section, development, splice and anchorage requirement. Horizontal reinforcement shall be anchored near the edges of the wall or in the confined core of the boundary elements. Splicing of vertical flexural reinforcement should be avoided as far as possible in regions where yielding may take place. This zone of yielding this zone of flexural yielding may be considered to extend for a distance of Lw above the base of the wall or 1/6 of the wall height, whichever is more. However, this distance need not be greater than 2 Lw. Not more than 1/3 of this vertical reinforcement shall be spliced at such section. Splices in adjacent bars should be staggered a minimum of 600 mm. Lateral ties shall be provided around lapped spliced bars that are larger than 16 mm in diameter. The diameter of the tie shall not be less than 1/4 that of spliced bar, nor less than 5 mm. The spacing of ties shall not exceed 150 mm on centers. Welded splices and mechanical connections shall conform to clause 25.2.5.2 of IS 456. However, not more than half the reinforcement shall be spliced at a section where structural yielding may take place. That's all about the design provisions for shear walls. Now let's look into an example. A shear wall for a two-story building shown in figure 2. This is figure 2. Has been designed and detailed in this section. The materials are M15 concrete and Fe415 steel. The unfactored forces in the panel between the ground level and first floor are obtained by analysis as given in this table. The maximum factored bending moment on the section is found out as 6,490 kilonewton meter, and the maximum factor shear force is 863 kilonewton. First of all, shear design. At section AA, the design shear force is 863 kilonewton, and let the effective depth in resisting shear be 3760 mm. Therefore, the TOV value is 0.998 Newton per mm square, and let the minimum vertical reinforcement, that is 0.25%, be provided in the web. Therefore, as per table 13 of IS 56, TOC equals 0.35 Newton per mm square. Hence, shear to be resisted by horizontal reinforcement is VUS equals 560 kilonewton. This requires a ratio of H by SB to be 0.413. However, provision for minimum horizontal reinforcement 0.25% requires this ratio to be 0.575 as TW is greater than 200 mm. The reinforcement shall be in two layers. Thus, horizontal reinforcement of 8 mm diameter bars at 175 mm center to center in two layers will suffice. An opening is present in this at section BB. This is section BB. Taking depth of wall on each side of opening, that is resisting shear as 1280 mm, TOB equals 1.466 Newton per mm square. Thus, shear to be resisted by reinforcement on each side of opening is VUS equals 328 kilonewton. Therefore, provide 8 mm diameter two-legged stirrups at 140 mm center to center on each side of the opening. These two sides. It's shown in this figure. The next is flexural strength of web. The vertical reinforcement in the web is 0.25%. The length of the wall LW is 4140 mm, and its web thickness is TW is 230 mm. Axial compression will increase the moment capacity of the wall. Therefore, the factored axial force should be taken as PU equals 0.8 times 1922.9 plus 1.2 times 250.7 equals 1845 kilonewton. Assuming this axial load to be uniformly distributed, load on web equals 1059 kilonewton. Thus, from equations in 1.3.1a, it can be found out that the moment of resistance of the web is 2967 kilonewton meter. The remaining moment, that is mu minus muv, shall be resisted by reinforcement in the boundary elements. Third one, boundary elements. The axial compression at the extreme fiber due to combined axial load and bending on the section is 6.805 Newton per mm square. As this is greater than 0.2 FCK, provision of boundary elements along the wall edges is mandatory. The center to center distance between the boundary elements CW is 3.760 meters. The axial force on the boundary element due to earthquake loading is 937 kilonewton. Thus, the maximum factored compression on the boundary element is 1494 kilonewton, and the factored tension is calculated as minus 675 kilonewton. Assuming short column action, the axial load capacity of the boundary element with maximum reinforcement of 0.8% is 2361 kilonewton. Therefore, 12 bars of 16 mm diameter will be adequate to take the compression as well as tension. The arrangement of reinforcement in the boundary element as per figure 3 requires 10 mm diameter rectangular hoops to be provided at 95 mm on centers as special confining reinforcement. And the fourth one, reinforcement around opening. The opening is of size 1200 mm by 1200 mm. The area of vertical and horizontal reinforcement in the web, 0.25%, that is interrupted by it is 690 mm square. Therefore, 1 bar of 16 mm diameter should be provided as per layer of reinforcement on each side of the opening. The vertical bar should extend for the full story height. The horizontal bar should be provided with a development length in tension beyond the sides of the opening. Figure 3. This figure shows the detailing of reinforcement in two directions at different sections. That's all about design and detailing of shear walls. Thank you.